So today we are going to be going through and discussing AC circuits. This is not on exam 2. This will be on exam 3. So understand that. Last time we went through and talked about the 4 different type of dependent sources. So we have our dependent voltage source where it can depend on voltage or current. And we have our dependent current sources, which depends on voltage or current. With it, there will be an equation right next to the source, and it will tell you where that current or voltage is in order to go through and determine the value for the source. So are there any questions on last time? So today we are going to talk about the sine wave. So this is going to be the most basic type of AC circuits. We're going to talk about the sinusoidal waveform, some of the terminology that's associated with the sine wave that we'll be using, some of the measurements that we're going to have, as well as the formula and how that is going to look for this class. Because it'll look a tiny bit different compared to what you may have seen for a sine wave before. So first, let's discuss what we will see inside of our circuit. So the symbol we'll be seeing is a circle with a sine wave inside of it. This is going to indicate that we have an AC source that follows a sine wave. If we have a different type of alternating current, you'll have a different shape inside of your circle. So if you have a sawtooth function, instead of being a sine wave in there, it'll be the sawtooth look. It's a square, it'll have if it's a square function, it'll have the square function in there. But in general, right, it looks like this, just the exact shape of the curve will be a little bit different. So with the sinusoidal voltages, or you can have sinusoidal currents as well. With these, they are produced by either rotating electrical machines, like an AC generator, or some sort of electrical oscillator circuit. So you can actually have a circuit that is oscillating that is then acting as the source for a different circuit. In order to go through and do that, we need to talk about some of the ways we can have oscillating circuits first. So that is going to kind of start next week, where we'll look at capacitors and inductors and how those function with them. So that's a little more on the oscillating circuit or electric oscillator circuit starting next week. So right now we're just not going to care about it. We are focusing purely today on what is the sine wave for this class, and again, how is that going to be treated. So there's a couple pieces of terminology that we'll need to look at. So here we have a nice little sine wave. And for this here, there are a couple different things that we want to talk about. So first is our x-axis. This is going to typically be time. By typically, I mean 99% of the time, it'll be time when we go through and talk about AC circuits. For the y-axis, this can be time or it can be current. It's going to depend on our actual source. So if we have a voltage source, it'll be voltage on the y-axis. If we have a current source, it'll be the current value. So we here have a couple different things that are important. So first off, right, we have our zeros. So this would be a location where either the voltage or the current value would be equal to 0. We then here have the positive and negative maximums included on here. So for a sine wave in general, or just a sine function in general, what is the maximum value for sine? Yeah, so for the, right, so sine equals 1. This is our max. And then for the negative value, right, sine of whatever inside equals -1. This is the negative max. So with this here, we're going to see that we aren't necessarily going to be dealing with just straight up one single term inside of it. So that's why I'm going to be leaving it empty here, is whatever is inside is making it such that sine is equal to 1 or -1. So let's talk about some of the terminology associated with these positive and negative maximums a little bit later. But these are going to kind of be the key points that we go through and reference as we go through and look at our sine function. So again, we're going to focus on it starting with the sine wave. We will see as we go through and look at it towards the end of lecture today. We'll see what we do if it's not, if it's still sine wave shaped, but not exactly starting at 0 and then going to +1, how we would go through and talk about that. But we're going to wait a little bit on that right now. We're going to assume everything we deal with is sine. So sine of 0, 0, sine of 180, 0, so forth. So when we are looking at the positive value, this is everything above our x value here. This is going to be the situation where here we are assuming our current is going in the clockwise direction. So we're going, the positive end is on top. We're following our conventional current, and it's going to go through and go into the negative. So this is going, the fact that we are in the positive sign area is telling us the direction. If we were to go through and look at the values, so at each instant in time, if we had our sine function set up correctly, we'd be able to go through and figure out what is the current value that is being output at that specific time. So that is what this graph here is. If we have the negative part of the sine wave, what do you think happens to the current? Oops. Yeah, so it's going to start going the other way. That's it. So instead of going clockwise, it now is going counterclockwise for it. And once again, we'd be able to go through, and if we knew the time in the equation for our sine wave here, we'd be able to go through and actually calculate the numerical value that is being output here. So what is something, if we're looking at both of these circuit diagrams, that you notice for the source?
I mean, it's a different source.
What do you mean?
Yes, the sine wave showing that it's AC.
Yeah, so it's AC for both of them. What else do we notice about it?
Polarity switch, obviously.
So we have, in the case of where we have positive, the positive is on top. The case where we have negative, the positive is on the bottom. So the polarity itself is flipping. What type of source is this besides the fact that it's AC? Is it voltage or current?
Multiple.
So it's voltage, and this is why it has the plus minus. For current ones, it's a little bit more awkward, and it's something that varies a little bit based off of what you have. But how have we been identifying a current source so far in this class?
Circle with the arrow.
Yeah, so typically what you would see if it was a current source is you just awkwardly have an arrow next to it instead, and that would flip directions depending on which part of the sine wave you were in. So with this here, the plus and minus is explicitly because we have a voltage source. If it was a current source, there is awkwardly an arrow nearby. But again, it would do the same behaviors where it's going to flip orientation. And because it's going to be flipping orientation, that would change the direction the current is going to flow. So with this here, we need to check the terminology that is used on this. So for the positive side, so when we're above, or if we were to plug in our value, our sine term is positive, right? It is calling it the positive alternation. Versus the other situation, right, is the negative alteration. So it's just telling us which way it's flowing. Again, they're just going to be opposite of each other. So if we had identified positive to be the other way, that means that when we go to negative, it would need to be flipped as well. It all just depends on how you're defining it to start. Any questions so far? So the terminology is going to continue on here. Two of the main terms that you are going to see are period and frequency. So period, which is going to be represented with a capital T, is the amount of time it takes for one complete sine wave. And it's going to have the SI units of seconds. So when we're going through to measure the period, there are typically two to three different places, depending on how you count them, that you would want to go through and choose to start looking at your wave. So if we look at the image here at the bottom, if we wanted to start where sine was equal to 0, we need to be careful of defining where our period is. So we need to do one full sine wave. So we need to go to our positive maximum, to 0, to the negative maximum. And this will be where our cycle starts to repeat. So for one period, it is one complete sine wave that we're going to be dealing with. So whatever time passes here, this is the period. Again, capital T here because this is a very specific amount of time that will be dependent on the type of source that we have. The other thing that we might be given is instead is the frequency, which we'll be using a lowercase f to indicate, and it is the number of waves per second that you would have. So it has the SI units of the hertz, which is the 1/seconds. And so basically what we would do is we would time for 1 second and go through and count how many complete or how many waves, sine waves pass through. May not be a complete number. If this is a number that you're looking at a graph to try to figure out, it typically is going to be in terms of 2 pi's, maybe 1/4 of a pi. So you'll have nice values to go through and identify, but not always going to be the case. But it's the number of waves per second. Does anybody know how they're related from a previous class? Yeah, they're the inverse. Period is equal to 1/frequency, or frequency is equal to 1 over the period. So if you have one, you can go through and you can find the other. This is something that we're not really going to be using today. Something we'll be using more so on Wednesday when we go through to talk about phasors. But, right, this is the time portions that are very commonly associated with going through and talking about our AC circuits. So if you go through and look at them, I think they're typically referred to in terms of the frequency more so than the period. So you might see like the source is 60 hertz. What that would indicate is it would be that case, it would have 60 sine waves passing through every second that happens. So that's flipping from positive to negative 60 times. Questions on period and frequency? So, right, we need to talk about sinusoidal voltage and current values. So with this, very often we're going to look at what is referred to as the instantaneous value. So that is the value at a very specific instant in time. So in order to do that, we do kind of need to know a little bit more information about our wave. And so we have another piece of terminology here, which is that the highest point that we are going to have is referred to as the peak value or the amplitude. So in this textbook, you will see peak value referenced over amplitude. This is something that circuits focuses on a little bit more. If you go through and look at other wave behavior type things like simple harmonic motion, sound waves, light waves, and things like that, you would see amplitude used instead. They are the same thing, it's just the highest value you can have. So it's when the sine term is going to be equal to 1. So with this here, right, for the peak value, this can be referred to as the positive or the negative value technically. Very often, we're just going to use the positive value as our reference because it's a little bit nicer than saying that your biggest value is negative something. So if you have a positive, typically we refer to the positive as the peak value. But the negative peak value, same value, just negative instead. Peak to peak is the value between these two different peaks. So in this case, right, whatever V3 is and V6, that would go through and have us find our peak to peak value. So with all of this stuff here, it's nice to look at specific values. However, if we wanted to go through and generalize our behaviors, we need to do a little bit more effort to go through and explain that. So we're going to look at what is referred to as the RMS value. So RMS here is going to have the same definition as RMS literally everywhere else you're going to see it. And we're also going to need to talk about the average value. The average value has a couple of little nuances with it, so we'll wait to talk about that. But for RMS, this is referred to as the root mean square, and it is referred to as the effective value of, in this case, our particular source. So we can have the RMS value for a current source and the RMS value for a voltage source as well. So just looking at this name here, what do you think is going to be associated with the equation?
Average square root
So this is going to give us a square root. Average of what though?
of a square.
By 2. Yeah, so we're gonna have a 2 show up, or I'm not gonna do the proof. I've done the proof once in class and somebody fell asleep. So if you want to see the proof, it is in Appendix D, or sorry, Appendix B of the textbook. I can also talk to you about it after class. Just figured, let's just not do that. So yes, there is an average. There is a square root in here. The number 2 is gonna pop up as well. Its formal definition for circuits is a little bit different compared to where else you will see it. The proof is the same regardless. But the RMS value of a sinusoidal voltage is equal to the DC voltage that produces the same amount of heat. It should be in a resistor. As does the sinusoidal voltage. So basically, if we were to take out our AC voltage source and put in a DC one, the power that is going to be dissipated is the same. See. This was at the point of time last night where my cat decided she was possessed by a demon and was meowing at me and standing on the keyboard. And I was trying to get her off, so I probably was a little distracted. But yeah, it should be DC voltage we're going through and do that. So if we took out AC and put in a DC, the DC, same power that's going to be dissipated. So the equations are going to look something like this. So here we have the voltage one and the current one as well. Current has the same definition, but you replace every voltage with current. So if we look at the VRMS value, so V here is our voltage. If you look up VRMS online, you will probably not get this voltage value. You'll probably get the speed of RMS value that is associated with thermodynamics. So just be aware that there's two VRMSs. One is voltage, one is speed values. Same equation though. So it's going to be whatever it is over the square root of 2 or 0.707 times that value. So here we have VP. P here is corresponding to the peak value. So if we were to go through and look at this graph here, VP is our positive amplitude that we would go through and utilize. So 0.707 times whatever the maximum voltage that voltage source provides. For current, 0.707 times the maximum current that current source provides. So that is one way to go through and do this. And again, this is a way to look at how effective are sources. This is different from the average value. They're numerically different values. Have different equations associated with them. And again, we're not going to do either of the proofs. So something that you can get for this RMS value is you can also go through and use it to find the peak to peak. I find this a very awkward piece of information that you can get from this equation, because if you have the peak value, you just multiply it by 2 anyway. I don't know why. The reason we should probably bring this up is technically sometimes we are given the RMS value. So that's where it comes from. But again, typically if you have RMS, you'll find the peak and then double it. So take that as you will, but the textbook thought this was important. But rearrange it, double it, and you're good to go. Any questions on RMS value? You'll be seeing this more on Wednesday when we go through and start discussing phasors. That's kind of where it's a little bit more important. Right, today we're just doing a lot of definitions and getting some concepts out of the way. We'll start applying them more so on Wednesday. So we're going to see this same graph again. We're going through and looking at the average. So what problems does that give us? What's the average of a sine wave? Why is it 0?
Equal amplitude on top.
Yep. So every positive point has a negative value as well. So when we're going through and doing the average, we are not going to look at the entire sine wave. Right, that's just 0. That's not very exciting. So instead, what we're going to go through and do is we are going to go through and we only look at half the cycle. So very often when we're picking which half of the cycle we're going to go through and do, we will pick the positive portion of it. We're going through and solving. That way we are dealing with positive values instead of negative. So by averaging this part here, we would be able to go through and use the average value for our source. And it turns out the equation looks something like this. It's 2 over pi VP, or IP, depending again on what type of source you have, or 0.637 times the peak value. So again, that peak value is going to go through and affect not just your RMS value, but it's going to affect your average value as well.
This average is gonna be the same as that other mean, root mean square thing.
No, they're different things, because right, that one is 0.707
Yeah.
and this one is 0.637. They correspond to different things. So the RMS is related to the amount of, I think the textbook calls it heat that's dissipated. It's related to the power. Whereas the average value is if I took this out and put in a totally different DC source, the behaviors are the same on average. So. Okay. All right, any questions before we try an example? So I want you with your neighbors to go through and solve number 8 here.
It's 25. It's 50.
No, we do not have a packet for this yet because it's mostly definitions today. And I just couldn't find the energy to make a packet last night.
Will this be on, because the lectures?
Yeah, I will, when I give you guys the packet, fingers crossed on Thursday. I'll have that in there. I'm just trying to figure out how do I want to organize this particular packet?
Is.
And I think you can figure it out based off of name alone.
Approximately. She said that's just something that is a foolproof, that's just that, yeah, that's just maybe, that's all it's about. So, yeah, we just. And volts. Yeah.
Does anybody need more time to plug in your values? All right. What is the peak and how do we know? Yep, 25 is the single highest point on the graph. Typically, when we talk about peak, we're gonna use the positive value unless explicitly asked for the negative peak. This would be 25, what units? Volts. All right, how do I get the peak to peak value?
By tail.
Woo. All right, so for RMS here, what should be the value I am multiplying by my peak value? Something times 25.
1 over square root of 2.
1 over square root of 2 or 7.07. You are welcome, and it is in fact typically encouraged to go through and use the 0.707 instead of using the entirety of the square root of 1/2. Don't ask. I don't know. That is just typically what you see encouraged is use this value here. So if you take this and plug it in and round it to 2 sig figs, what should you get?
18
18 watts.
volts.
So for the average, still gonna have my peak value of 25 volts. What should the constant in front be?
Over pi.
Again, we're typically gonna want to start with the numerical values. So what is it?
60%.
So rounding that to 2 sig figs, what should you get?
So they don't want you to use the,
you have to
higher the 1/square root of 2, they want you to use what it.
So typically what I have seen, because this isn't,
Yeah.
so for RMS in general and averages for things like sine waves, I typically see it being encouraged that depending on your profession, depends on how many sig figs actually matter. For almost everybody, 3 is enough. So that's why we typically start with those as it is. If you need something that is more precise, they will have cutoffs for what they use for 1/square root of 2 or 2/pi.
Okay.
So in general, this is good enough to go through and use. So that's why we start with it.
Okay.
But when you plugged in your numbers, it should have still rounded to this, even if you
Yeah.
used everything. Any questions about 8? You guys good? So again, right, we can just use our equations directly. I promise you it gets worse from here. So please enjoy it while it lasts. All right, so we want to go through now. We are gonna probably fly through this part because I'm going to assume you guys know how to convert between radians and degrees. The reason we're gonna see this is sometimes with our sine functions, they'll be given with radians and sometimes degrees. So we need to make sure that we understand if we have big stuff given to us, how to go through and deal with that. You guys have a question? Okay, so to go from degrees to radians, you multiply by pi, divide by 180. That will give you your radians value. To get from radians to degrees, you multiply by 180, divide by pi. Or you can do the 362 pi. Right, your choice for that. So those are the conversions. This textbook is typically going to give us stuff in terms of nice angles. So we'll see a lot of 30s, 45s, 60s, and their counterparts in the other quadrants as well. Typically what we're going to be seeing, not every textbook does this, but this one's kind of if you could do it for the nice angles, you can probably do it for the not so nice angles as well. So the only time we're really going to need this is when we go through to look at phasors, which we will be doing on Wednesday. We'll want to make sure that everything is in radians. Today, it's not really going to matter. So whatever method you like to convert them with, go through and use that. But again, we'll typically have nice angles for that. So we want to go through, we and I want to focus on the actual function for the sine wave, how we're going to see it in this class, and what that is going to represent. So if I told you you had to write an equation out for a sine wave, what would that look like to you? You guys ever had to do the sine wave?
Do you mean like series?
Well, not a series. Let's not do it as a series. When you guys integrate like a sine, have you guys ever done it with a constant in front?
Yeah, yes.
So what does that roughly look like? A sine what?
What they,
But yeah, you just need to do that.
Right, so that this is the most basic form of sine, for the sake of argument. Do you guys wanna do this? What do you wanna call the left side of the equation that we're calling it?
it is. X.
Sine.
Sure.
Yeah.
Sure, f of x. Which is awkward because we have theta, so it should probably be f of theta.
Oh, my apologies, theta.
That's fine. I'm just saying we should probably. We'll see theta can be more complicated, a little bit later, so it might not always be, with that. Right, this is probably the first time you saw a sine roughly what it looked like, right? A sine theta. And if I was to go through and do this and I plugged in 0 degrees, my function should give me 0. And if I was to plug in 90, my f theta would be equal to A. And I can go through and I can just plug all of that in. I could do it in degrees, or I can do it in radians, so I could use 0, pi over 2, again, whatever it is. So with that, there is some terminology that this textbook is going to use. Again, this isn't on exam 2, but you might want it on your note sheet for exam 3, which is the terminology that is associated with this here. So if we look at the 0 degree part here, it is called positive going. That is the terminology to tell us that we're going from 0 to positive 1. That is what positive going means. You have the positive peak, so that's at 90 degrees. That is our amplitude, right? We can call it that as well. Again, this textbook's typically going to refer to as peak, but others you might see amplitude. We're going to then go down to 0, and then we reach the negative going portion of the graph, right? We are going into the negative. We then hit the negative peak or the negative amplitude, and then we're going to go through and we're going to re-enter positive going and and we're going to repeat this over and over and over again. So in this textbook, you will see your, sometimes you'll have to go through and you'll create your sine function. So if it says positive going, that means you're kind of in that first 0 to 90 degrees part. And if you see negative going, you're typically in the 180 to 270 degrees portion. That's typically how you're going to see it represented. So with it, you're going to have to be careful with reading your questions to understand what it is trying to have you do. Looking at the parts between 90 and 180 and 270 and 360, typically the wording is going to be a little bit different in comparison. So for this part of the textbook, it's going to focus on 0 to 90, 180 to 270. That's going to be kind of where the focus is for now. When we go through to look at phasors on Thursday, that's going to be where we can start kind of wherever we want, but the method is going to be a little bit different. So focus on that more so then. So what if we don't start at 0? What if we don't start at cosine?
Plus, whatever.
Yeah, so I don't remember what they call it in math, but it's called a phase shift. So a phase shift is going to be starting somewhere, in the case of sine, not at 0. So if we're starting at +1, or the positive amplitude, that would be a cosine situation, right? Your phase shifted 90 degrees. If you're starting at -1, right? That's a negative cosine. So you're either shifting your cosine by 180 degrees or you're shifting your sine by 90 degrees as well. We'll talk about direction here in a second. So with the phase shift, in this textbook, we are going to be seeing the Greek letter phi represented for that. So as a heads up, there are two different types of phi depending on where you go through and look. This textbook is going to use the straight line down through it. The other sources are going to use this version of phi, where it's kind of one piece instead. So you kind of curl through and then have the line go straight down. I will do my best to match the textbook notation. I also just prefer that phi anyway, so that's fine with me. But understand if you look elsewhere for phase constant stuff, you might see the other variant of phi. So here we have two waves. We have B and A. So what is A here? If we just wanted to look at the A without worrying about the stuff at the bottom.
Times.
And what is B?
Cosine.
So they are off by 90 degrees from each other. So depending on which one we would want to focus on is going to determine on what terminology we would go through and use. So if we look at the bottom here, it gives us kind of that terminology that we'll be seeing. We're going to have leads and lags. So if we were saying, focusing on B, B leads A by 90 degrees. It is starting 90 degrees ahead of A. So it's starting at cosine instead of sine. If we were focusing on A, given stuff about B, we would say that A lags B by 90 degrees. And so with this leads and lags, it's going to depend on which function we actually care about. And so again, if we're given A and want to find B, we would use B leads A by 90 degrees. If we had B and wanted to find A lags B by 90 degrees in this particular case. Will not always be 90 degrees. Very often we'll have 30 degrees. Again, nice angles. So 30, 45, 60, maybe 15, like those degrees there. Any questions about the terminology for phase of a sine wave so far? Oops. Oh, there goes all those animations. All right, so, this is the general one that we'll be seeing in this textbook. We'll see y is equal to a sine theta, where y is going to really be equal to v or I. So if we have a AC voltage source, y here is replaced with v. If we have a current AC source, y is replaced with I. V here is just the general situation. If we need to include a phase shift, we are going to have a plus or a minus or plus phi inside of our sine function. So here we have y is equal to a sine theta minus phi, and here we have y is equal to a sine theta plus phi. So this phi here portion, this is the phase shift that we have. Again, it will depend on what exactly we have or what we're given to determine the sine. So we will use negative phi when the sine wave is lagging or when that it's shifted to the right. When the sine wave is, we'll use theta plus phi when we are leading or the wave is shifted to the left. So depending on what we have will determine on if we're using negative or positive values. Okay, so if we go back to this one here, with going through and looking at it, right, we can kind of see where that's gonna come. So let's focus on the situation where B leads A by 90 degrees. All right, so that's gonna be the one that we wanna focus on here. So if I'm looking at leads, that is gonna be the situation where I have the plus 90. So what I would have is right, we'd have A sine. Oh, sorry. Hold on. So if, right, I can write it either of these ways, depending on which of the situations that I have, right? One's positive and one is negative. So if you don't know which way to go, right, we can go through and we can do the analysis kind of backwards to help us figure it out. So let's say hypothetically, I wanted to go through and I wanted to go from sine to cosine and go through and do it that way, right? It's going to be one of these. It's going to either be positive or negative 90 degrees. Why is it negative?
Is your amplitude over? Have to be, could it be positive?
Yeah, positive.
So if I plug in, right, for cosine, right, if I was to plug in 90 degrees, I should get 0. Right, for cosine? But for sine, that should be positive 1. So if I'm looking at these here, right, if I plug in sine of theta equals 0, just in general, right, that should give me 0. So if I was to, but if I'm at 90 degrees, I want to figure out which one of these gets me a value of 0. Right, so if I plug in 90 into this one, right, that's going to get me 180. That should get me 0. If I do 90 for this one, it also gets me 0, but in different ways. So with it here, maybe we should go back to the picture. So if we focus on B leads A by 90 degrees, well, let's focus on that one. So B is shifted. So B is the leader. A is the lagging one. So if we look at the terminology here, so if it's lagging is going to be when I use the negative. So leading, so this one would be B in comparison to that example there. So we would use the neg. I don't know why I wrote these upside down. Oh, sorry, it's positive. I wrote them flipped from what I had over there. That's my bad. So right, it's gonna be this positive one here because it's leading. So anytime you see leading, that is gonna indicate that you're gonna be using the positive value. If you see lagging, that should indicate to you that you're using the negative.
So is that that's leading actually lagging? Like in the term that we know those words as?
Yes,
Okay. Is that kind of backward?
yes.
Is it A, so is A sine theta like plus 90 equal to A cosine theta? Or
It'd be, yes.
visual and just push it again.
Is it the circle, the moving circle one?
No, I just pull up on decimals. I'll just do plus.
Okay.
Something.
There's I should have put it in here. I didn't because I thought it might be more confusing. There's a fun, circle diagram that moves around. I'll see if I can find it after class. If I can, I'll post it, in the after, below the video.
This one is.
Yeah.
Cool.
So. Again, not for exam 2, but for exam 3, you might just want to write. Next to these leads versus lags for when to use them. Typically with the questions that we have, it is very clearly one way. It will say, this one leads that one, or this one lags that one. It'll be one option. For, yes, leads is the positive and lags is the negative. So. Again, when we have this here, it will always show the same, or the textbook will always be very clear. It's one way for going through and doing. So would you guys like to try, are you guys ready for an example for writing out this equation? So we are gonna try 17 here. So the general way that you see the equation represented in a lot of places is you would have a sine theta minus plus 5 is typically how you see this represented. It's just kind of the most general way that this represents all of it at once. So I want you to work with your neighbors to go through and figure out what should the A value be, what should the theta value be, minus or plus. And then go ahead and solve for the third, and then we'll do a little check-in, and then we'll see how to solve these values.
Say something.
Minus there.
We'll double once on top of the sine A. Sine
Okay.
So there's something. There's
And 90.
subtract.
You subtract, it's like, wait, that's like subtract. It lags.
And. Cause out for 105 is 30.
Yeah. That one. Wait. See that?
Does anybody want more time working on 17? Okay,
What is the constant A represent?
A represents the amp, so. A is used to represent the amplitude, but in this textbook, it is gonna refer to it as the peak. So if we. So if we look at this one here, the positive amplitude is the positive peak value. But in general, you'll see A used, but, this class was gonna refer to it as peak. Does anybody want more time? So what should my amplitude value be? Be 15 volts, so we have a voltage source here. And what should theta be?
Either
Tell me.
things.
Yeah.
It's a 30, 40.
Yes. Mm-hmm. And so it's be the 30, 45, 90, 180, 200, 300. And so then what is phi? We're just in general, what is the angle? Yes, 30. So before we do the positive, negative, we first want to assess if we're gonna have a positive or negative sine function to start with. How do we know which one we have?
Positive point. Positive. That's all.
So this is gonna indicate that we have a positive sine function. So now we need to talk negative or positive.
Doing negative
Why?
because B is the one that's. A is trailing after B, but A crosses at 0, so it makes
So-
B ahead of A.
So it says lagging. So lagging indicates negative. That's all we need to do. Is look at it, say, oh, the sine wave is lagging. That means we are gonna use the negative value. So that means the general form for this here is we're gonna replace Y with V because this is gonna be a voltage. I'm just gonna write it out twice. We're gonna have A sine theta minus phi. And so when we go through and look at this, because we're gonna plug in a bunch of different theta values, we'll have 15 volts sine theta minus 30. Questions? Right, so we just have the fun privilege of going through and plugging in a bunch of numbers. Right, at this point, so we'll need to do 30, 45, 90, 180, 200 and 300 theta. If we're looking at this question, all of our values are in degrees, which means that we should probably be solving sine in what mode on our calculator?
Degrees.
Degrees.
Unless you're gonna do version.
Doing it in degrees. Unless you really wanted to go through and convert them all. So before we just go through and start slamming in a bunch of different numbers, the reason it tells you that B has a peak of 15 is you're gonna be doing 18 for your homework, which is gonna make A lead B instead. So that is why, it's given that way. Or I can't remember if A leads B or B lags A. Same idea, it's just, it flips, what's happening. I just forget how it's worded. All right, so we're gonna go through. And we're just gonna do all of these here. So we're gonna, for the sake of argument, I'm just gonna write 15. We know that's 15 volts. I'm gonna have 30 minus 30, so that should give me a grand value of.
0.
I'm gonna have 15 sine 45 minus 30. So let's do this for 2 sig figs. What should this be?
3.9.
These are in volt. Oops. I'm just gonna write all of these out and then I'll just ask you guys to go down the list. Just give me 1 second. Oh my goodness. Yep, hold on. Let me mess that up. Right, minus 30. We'll have 15 sine 180 minus 30. 15 sine 200. And I'm just gonna add a new slide here so I stop canceling the slideshow. Oops. And then we'll have 15 sine 300 minus 30. All right, so when I have 90 degrees for 2 sig figs, what should my voltage be?
13.
180? 7.5? 200? And 300?
50.
Someday my pen will just work throughout the whole thing. Anyway, I'll write those numbers in, if my tablet unfreezes itself. But are there any questions on 17? 18, it's the opposite way, but just again, make sure, double check how the question's worded with how you would go through and solve that. So with everything we've talked about today, this is setting up the basis for going through and talking about phasors. So with phasors, we are going to be taking this sine function and we are going to be splitting it into 2 components. One of them is going to be associated with imaginary space. So we're doing some imaginary stuff on Wednesday, numerically. So maybe do a quick read over on that stuff. You should have covered imaginary numbers before. We'll cover some aspects of it, but not necessarily all of it. So that will be what we are doing on, or not Wednesday, Thursday. So that's all I have planned for this. My tablet is currently frozen, so I can't get out of this, but I'll write the answers on here before I go through it. So if you would like to come to class tomorrow, you're welcome. But you do not have to. It's just going to be more review time for the exam.
So I said, I didn't respond to your. Basically, yes. Yeah.